Question number 1. Given the following value of pKa and pKb, select the strongest acid from the one list below. If you have a log Ka, you have a stronger acid. We also say if you have a smaller pKa, you have stronger acid. So here you're actually looking for the strongest acid, right? And it lists a lot of pKa value here. So you need to actually select the one with the smallest pKa value, right? So if you examine these things, this pKa is 3.37. This one is 8.69. This one is 7.53. Okay. So the strongest acid will be the one with smallest pKa. Therefore, we know the answer is HNO2. So here you can see there are actually two species. It doesn't give you pKa, right? But you can actually compute the pKa from the pKb, right? Because you know the pKa plus pKb is going to equals 14 as well. If you compute a pKa of, let's see, C5H5N, okay, 14 minus that is 5 point something, close to 6, right? And then the other one is 8 point something, so it's actually pretty big, right? So you know they won't be your answer either. Everybody fine with this? Okay, so then I'll ask you, who is actually the strongest base? So you want to know, okay, so if you just compare these two, then definitely you will say NH2 is actually the stronger base, right? But how about the HBRO? The pK is 8.69, right? What is the corresponding pKb? 5 point something, right? Yeah, so it won't be the strongest one because the NH2 is actually 4.75. All right? Okay, so let's actually the question number 1. Okay, so make sure you have this concept. The smaller the pKa, the stronger the acid. Okay, the smaller the pKb, the stronger the base. All right. Question number 2. What is the OH minus in a solution that have a pH of 12.50? Okay, so this question is basically testing whether you know the definition of pH and pOH, right? I know pH plus pOH is going to equals to 14. Therefore, my pOH is going to equals to 14 minus my pH, which is 12.5. They give me a value of 1.5. Okay, so pOH we know is defined as negative log of OH minus concentration, and it's going to equals to 1.5, right? Therefore, I know my OH minus concentration is going to equals to 10 to the negative 1.5. And then once you do the calculation, you should get a value of 0.0316. Okay, so there will be 3.16 times 10 to the negative 2. Okay, so there will be actually your OH minus concentration. Next one. Give the conjugated base of HSO4 minus. So give the conjugated base of HSO4 minus. Okay, so this sentence tells you the HSO4 minus, this should be the acyl base. Acid, right? So you know this is actually the acid. And you want to figure out its conjugated base, right? And then we know the difference between the acid and base is that acid has one more proton, right? So that in order to get the conjugated base, all you need to do is actually you want to minus a proton from the original equation, right? So once you do that, you should see that its conjugated base should be SO4, 2 minus. Okay, so another conceptual or definition question. Next, calculate the pH of 0.5 m solution of ammonia, where the Kb is 1.8 times 10 to the negative 5. Okay, so right now we're actually entering the pH calculation. Okay, so every time when you see this keyword pH, the first question you should ask yourself is like, what kind of solution that you have, right? So what kind of solution do you have? Weak base, right? So write out the OH minus concentration. Okay, it's going to equals to square root of your base concentration. What's the value? 0.5, right? Times your Kb, 1.8 times 10 to the negative 5. Okay, make sure you operate your calculator correctly. You should be able to get your OH minus concentration is going to equals to 0.003. Okay, therefore you can calculate your POH, negative log 0.003. Okay, and then it's going to give you a value of 2.52. Okay, then you can write out your pH equals to 14 minus your POH equals to 14 minus 2.52. Therefore, you get the value of 11.48. Okay, so let you know your pH equals to 11.48. Okay, so question number 5. At a certain temperature, the percent dissociation of an acid. So you know this is actually a weak acid solution, right? This weak acid is HClO2. Okay. From the description, you know your percent dissociation is 10%, right? That means it's equals to 0.1. Okay. So the next thing you do is actually to write out the definition of percent dissociation. Okay, so we know the percent dissociation is the proton concentration over your weak acid concentration, okay, times 100%. So how do you actually represent the proton concentration of a weak acid? Right now, you should know your proton concentration of weak acid should be the weak acid concentration times your Ka, right? And take the square root of that. So this is something that you should translate. Okay. And at the denominator, you still have your HA naught. So this thing is actually going to equals to the square root of Ka on the top, HA naught at the bottom. Okay. And you know this whole thing equals to 0.1. How do I go from here to here? This one to here. So you guys are not familiar with this operation? So the A, are you guys familiar with this? Yeah, this is like the simple calculations. So once we do those operations, this is actually this actual equation you're going to get. Okay. So this question is asking for what? Right? You want to calculate Ka, but it tells you the concentration of your weak acid is 1.63. Okay. So this actually tells you your weak acid concentration is 1.63. And you want to calculate the Ka. Okay, so what you do is actually just plug in. So this can be written as the square root of Ka over 1.63 is going to equals 2.1. Okay. What you do next is actually you square on both sides. Okay, so it will be Ka over 1.63 is equals to 0.1 to the second power. Therefore, your Ka is going to equals to 1.63 times 10 to the negative 2. Okay, and this is actually how you get the answer. All right, question number 6. What is the pH of a solution prepared by mixing 50 ml of 0.1 m NH3 and 25 ml 0.1 m NH4Cl assuming that the volume of the solution are additive and the Kb of amine is a certain number. Okay. So again, you see the keyword pH shows up again, right? So currently you want to calculate the pH of this solution. So the number one question is actually you want to ask yourself, what kind of solution do you have? Okay. So what kind? It's a buffer solution. How do you know? Yeah, so you want to actually look at the species, right? So this is actually species number one. That's species number two. They look somewhat similar, right? So the NH4Cl, we know once it dissociate, it becomes NH4 plus Cl minus, right? NH4 plus is the conjugated acid of NH3, right? So that means inside your solution, you're going to have a good amount of NH3, a good amount of NH4 plus, and these two are conjugated acid and base pair, right? So this you have less situation, then you're going to have a buffer. Okay. So now you know you have a buffer. You want to calculate pH of a buffer, then you go to the HH equation, right? So HH equation is what? pH equals to pKa minus log. You want to put acid on the top, base at the bottom. Okay. So once you know you want to use HH equation, right? The first thing is what? pKa, right? Do you have the pKa value here? You don't, right? So what do? Divide Kw by Kb. Oh, yeah. Okay, so Ka is going to be Kw over Kb. Kw is actually 10 to the negative 14. Kb is 1.8 times 10 to the negative 5. Once you do that calculation, you should be able to get the value of 5.56 times 10 to the negative 10. Okay, so let's set your Ka value. Okay, therefore, your pKa is going to equals to negative log 5.56 times 10 to the negative 10. You're going to get a value of 9.26. Okay, so you know the first term you're going to put in is actually 9.26. Now the next thing you want to actually compute is actually the ratio between your conjugated acid over base, right? So you want to know what is the concentration of lead. Okay, so it says you have 50 ml of the base, right? So this is actually the base. That is actually your acid. So the concentration of your base, I put A minus here, is going to equals to the mole of your base, which is 50 ml times 0.1 divided by the total volume, right? Total volume will be 50 plus 25. Okay. Concentration of your acid will equals to 25 times 0.1 divided by 50 plus 25. Okay. The things that you really care about is actually the ratio, right? So you know the acid over base is going to equals to this overlap. So what you're going to have is 25 times 0.1 divided by 75. That's actually your acid. Base will be 50 times 0.1 divided by 75. Okay, this will cancel out. So you end up with just 1/2. So you know the ratio of your acid over base is just 1/2, right? So the next thing you do is actually you plug this back in right to here. Okay, so let the pH is going to equals to pKa negative log acid over base. Okay, so your pKa is 9.26 minus log 1/2. Okay, so once you do that calculation, you are going to end up with a value of, so this is actually 9.26 plus 0.3 equals to 9.56. Okay, so this is actually how you get the pH of this buffer solution. Okay, the key here is really, can you actually identify the buffer? Because if you can, then you're going to use the HH equation, right? The second thing you should know is actually, can you actually compute your Ka from Kb? So you can actually compute your pKa, right? The third step is actually you need to know how to calculate the ratio between your conjugated acid over base. Okay, so you can actually calculate the moles of your acid, moles of your base, then you know the ratio between them. Okay, then you plug them all back into the HH equation, then you can get your pH. Okay, so this is actually a logical flow how to solve this type of questions. Okay, calculate the pH when 0.68 gram of C6H5COONA is added to 18 ml of 0.5 m benzoic acid, C6H5COOH. Okay, ignore any change in volume. The Ka value of the benzoic acid is 6.5 times 10 to the negative 5. Okay, keyword here again, pH, right? So pH, once you have pH, it's keyword. The first question you ask yourself is, what kind of solution do you have? Right? So what kind? Buffer, right? How do you know it's buffer? Okay, so by now you should see that these things is actually this, right? C6H5COO minus. Okay. So this species and this species, they are conjugated acid and base pair, right? Since you have the similar amount of conjugated acid and base pair, therefore you know you have a buffer solution. Okay, buffer solution again, HH equation. Okay, pH equals to pKa negative log acid over base. Okay. First term, Ka. Do you have Ka in the question? You do, right? So the Ka is 6.5 times 10 to the negative 5, right? Therefore, you know you can compute your pKa. Okay. Then we need to actually focus on the second term, right? So the acid concentration. Okay, so the acid is your C6H5COOH, right? And the mole of your acid will be 0.5 times 18. Okay, that's how many moles you have. Okay. Both the constant volume is actually 18. Okay. Base. Base. Okay, first, you know, it did not give you the concentration, it only give you the weight of your base, right? So the first thing to do is actually to compute the number of mole of the base and then the concentration of the base, right? The mole of the base will be 0.68 divided by the molecular weight is 144.1, then divide by 18, right? That's the concentration of your base. Therefore, when you compute your HA over A minus, it will equals to 0.5 times 18 divided by 18. Bottom one will be 0.68 divided by 144.1 divided by 18. And this will cancels out, okay? And then the things on the top will be, okay, what's the number that I get here? Okay, so once you compute all those things, so I didn't actually compute this number. Okay, I actually plug it in and then compute the overall. So pH is equals to pKa, which is negative log 6.5 times 10 to the negative 5 minus log this whole 10. Okay, when you do that calculation, you should be able to get a value of 3.91. Okay, so I'm sorry I did not actually calculate this number, but that's the overall process. Okay, so again, key is really, can you actually recognize what kind of solution that you have? Calculate the pH of a solution prepared by adding 20 ml of 0.1 m HCl to 80 ml of buffer that is comprised of 0.25 NH3 and 0.25 NH4Cl. The Kb of lead amine is a certain value. Okay, so what kind of solution do you have? A buffer, right? So how do we calculate pH? HH equation, yes. pH equals to pKa negative log HA over A minus. Okay. Everything is fine? Okay, so I actually like your response. Okay, but there's actually one more thing I feel like everybody missed. Okay, first one, yes, apparently you're actually adding a strong acid into a buffer, right? The things I want to make sure is actually I indeed have a buffer. Okay, if I can say I indeed have a buffer, what I mean is that the amount of phase inside your buffer must be way more than the strong acid you add in. Okay, if you add in more strong acid than the conjugated base that you have inside your buffer, all you have will be a strong acid solution. Okay, but the acid concentration to be actually recalculated. Okay, so the first question is actually you want to actually really know what's the mole of your strong acid and what's the mole of your conjugated base, right? So we can do a very simple calculation. The number of mole of your HCl is 0.1 times 20, right? So that's 2 millimole. The mole of your base in this case is NH3, right? Concentration is 0.25. Volume is actually 80. Okay, so this actually tells you have 20 millimole of a weak base, right? So your strong acid will be fully consumed by your base, right? Once it's actually fully consumed by your base, what are you going to get? The moles of your NH4 plus. Okay, originally you have 0.25 times 80 as well, right? So you also have 20 millimole of the NH4 plus before you add in the acid, before you add in the strong acid. Okay. But right now you know your strong acid, 2 millimole of your strong acid will be fully consumed by your weak base, right? Therefore, you know in the end, the number of mole of your NH3 will equals to 20 minus 2, which is 18 millimole. Once that happens, you're going to have more conjugated acid. It will be 20 plus 2, which is 22 millimole. Okay. So this is actually something that you need to actually get used to it. Okay. When you add a strong acid into a buffer, then you know your weak base will be consumed partially. Okay. Its conjugated acid will increase by a certain amount. Okay. So these are the things that you need to know. Okay. So once you have this, then you can actually compute the conjugated acid base ratio, right? This will simply equals to acid will be 22, base will be 18. Okay, so you kind of know what to write for your second term in the HH equation. Okay. Now the only thing is actually you just need to figure out the first term, right? So since you don't have Ka provided, you need to compute your Ka using Kw over Kb, which equals to 10 to the negative 14 over 1.8 times 10 to the negative 5. Okay. All right, so it's 5.56 times 10 to the negative 10. All right, so with this, then you can write your pH equals to pKa, which is negative log of 5.56 times 10 to the negative 10, negative log, acid over base, which is 22 over 18. By doing this calculation, you're going to get a final value, pH equals to 9.17. So any question for this? Okay, so what would you do if that's the case? It's a good question, right? Let's just do this hypothetical question. Let's say you have, so here we have 20 ml, right? Let's say we have 1 liter, 1,000 ml. Okay. So now you have 1,000 ml of HCl into the buffer. Okay, so if that is the case, you know you need to rewrite this here, replace that 20 with 1,000, right? Therefore, you're going to have 100 millimole, right? So you can see that 100 millimole is actually outweighing than any of the weak acid with base, right? Okay, so still you will be consumed by your weak base. Okay, therefore you know once it got consumed, let me change the color, otherwise we are confusing ourselves. Therefore you know your after interaction, right? This one will only have 100 minus 20, which is 80 millimole. Okay, and then your amine, this one, okay, the mole of your NH3 will be fully consumed, right? So you don't have this. The mole of your NH4 plus will equals to 20 plus 20, right? And that's equal to 40 millimole. Okay. So right now you have what? You have a strong acid and a weak acid coexist inside your solutions, right? So NH4 originally have what? 20 millimole, right? Okay. The base is also 20 millimoles. The base will be consumed by your strong acid. So all your base will be gone, right? And once your base got the proton, okay, it becomes the conjugated acid, right? So this guy will become this guy. That's why I write 20 plus 20. Okay, so conjugated acid base is kind of like equilibrium. Okay, one decrease, the other one must be increased. Okay, because the proton is actually play the role here. Okay, everybody see this now? Yeah. Very good question. So what if I add water? Water is actually a very interesting species, right? So what's the pH of water? Everybody know the pH of water is 7, right? What does that mean? The proton concentration inside water is 10 to the negative 7. Okay, so if today you have acid that produce a proton, its concentration is below than 7, negative 7, sorry, then water will be actually the dominant species. Okay, then it's not going to affect the pH of your water. All right. Yeah. So here is actually a case that I think actually nicely actually summarize many of the concept. Okay. You're adding a strong acid. Okay. Then you consume all the, you're adding actually excess amount of strong acid. It's going to consume the weak base completely, right? So all your weak base converted into its conjugated acid. Okay. That's why we put 20 plus 20 for the NH4 plus, right? So now you have strong acid and weak acid coexist inside your solution. Okay, who is going to determine the concentration, the pH of the solution? The strong acid. Okay, because strong acid is going to dissociate 100%. Weak acid is actually only going to dissociate a little bit. Okay, so when you are going to calculate the pH of this solution, all you need to know is actually what is the concentration of your strong acid. Okay, so how do you calculate the strong acid concentration, which HCl concentration will be, you know, the mole is 80 millimole, right? What's the total volume? It's 1000 plus 80, right? 1000 plus 80. Okay, so if you do that calculation, what is that number? 0.074. Okay, so this will equals to your photon concentration. Okay, because strong acid, right? 100% dissociate. That concentration will give you the proton concentration. The pH will simply equal to negative log of 0.074, which is going to give you a value of 1 point something, 1.13. Okay. So you need to know what is the solution that you have. Okay, and then based on the equation we give you, follows 5 different solutions to compute the corresponding pH. All right. Next one. Determine the volume in ml of 0.71 m KOH needed to reach half equivalence point in the titration of this. Okay. So keyword titration, right? So every time when we say titration, the first thing you do is what? Find out who is actually your titrant, who is your analyte, right? The titrant is what? KOH, right? The way you know is because the titrant can only be strong acid or strong base, right? So apparently right now, the only things KOH is actually the strong base here, right? Analyte will be HClO, which is actually a weak acid, right? So let's actually the first step. Second step is to determine the equivalence point, right? The way you figure out equivalence point is that you use the concentration of your titrant times the volume of equivalence point is going to equal to the concentration of your analyte times the volume of your analyte. Okay, concentration of titrant is what? 0.781, right? BEP is actually the one you are looking for. Concentration of your analyte is 0.494. Volume of your analyte is 49.8. So by doing that, you know your VEP is simply equals to 0.494 times 49.8 divided by 0.781, which give you a value of 31.4496. Okay, so let's actually the equivalence point, right? If you read the question, it's actually asking you for the half equivalence point, right? So the half, okay, we call it V half, or equals to VEP divided by 2, which equals to 31.4496 divided by 2. That's going to give you a answer of 15.7. Okay. So that's actually the answer you're actually looking for. Okay, any questions for this? if you don't have question for this, okay, I have a question for you. Okay, if you are actually at half equivalence point, okay, which is at zone 2, right? What kind of solution do you have? A buffer solution, right? If I ask you to calculate the pH of these things, can you calculate it? Buffer, HH equations, right? So pH equals to pKa negative log weak acid over its conjugated base. Okay, so you know how to calculate the pH of these solutions, right? Do you have the Ka? You do, right? So you know how to calculate the first term, right? Second term, what is the concentration of acid over base? It's a very interesting question. Okay, this is actually, if you think through it, it becomes super easy. Okay, so what does it mean by equivalence point? You have the same amount of titrate and aniline, right? So in the beginning, you have all weak acid. Okay, once you hit your equivalence point, all the weak acid will be consumed by your titrant, right? So all you have will be its conjugated base, right? So in that case, your A minus, okay, concentration can be computed. Okay, but here, where are we? We are at the half equivalence point, right? That means half of your weak acid will be consumed. For what it produces? The same amount of its conjugated base, right? So that means it's actually your weak acid over its conjugated base, the ratio will be 1:1, right? So since the ratio is actually 1:1, the negative log of left 1 is going to give you a value of 0, right? So the pH will simply equal to your pKa. Okay, so at half equivalence point, pH is going to equal to pKa. Okay, so this is actually something extra that we did not really emphasize in the past, but I think now it's good time for you to know. Okay. All right, so let's actually how you solve question number 9. Okay, number 10. Okay, so this is actually more conceptual thing, so let's actually know much computation you need to do. Okay, so let's read through this. Aniline has a Kb of this value. Okay, if every time when I see this sentence, the things I will write is actually the aniline is actually a weak base, right? A weak base, okay, if 100 ml of 0.5 N aqueous aniline solution is mixed with 100 ml of 0.5 M of hydrochloric acid. What's hydrochloric acid? Strong acid, good, okay. And it asks you, is the pH going to be larger than 7, equal to 7, or smaller than 7? Okay, so we know you have a weak base, right? Plus a strong acid. This is going to produce what? It's conjugated acid, right? So you have a weak base inter with a strong acid H+, that's going to produce the conjugated acid of the weak base, right? So then you look at the amount, 100 ml, 0.5 M, 100 ml, 0.5 M. That means actually what? The same amount, right? So they're going to consume each other, right? So all the weak base will be consumed by less strong acid, right? Therefore, all you have inside your solution will be a full of conjugated acid, right? So it's actually a acidic solution. This is actually acidic solution. Therefore, the pH will be less than 7. Okay, so the answer is actually less than 7. Okay, so let's actually trying to test you. Okay, do you have the concept that if you have a weak base inter with a strong acid, it's going to generate its conjugated acid of the weak base. Okay, if you add in the same amount of weak acid and weak base and strong acid. They are going to consume fully with each other and produce only the conjugated acid on the other side. Okay, and since you have a weak acid in your solution, therefore the pH will be lower than 7. Okay, so that's how you solve number 10. Okay. Calculate pH of 0.5 m solution of sodium acetate. The Ka of the acid is 1.8 times 10 to the negative 5. Okay. So the key thing here is actually to know what kind of solution you have, right? This one is going to dissociate, produce Na plus and CH3COO minus. Okay. So let's take the first step. Okay, you should know. Okay, then you need to ask yourself, what kind of solution do you have? So the Na plus, Na is 1A group, right? So it's going to be neutral, right? Na is actually neutral, right? How about this? Basic, right? So you have a weak base here. So you have a weak base solution, right? Therefore, OH minus equals to the square root of weak base concentration 0.5 m times Kb, right? Because right now you can compute the OH minus. So Kb, do you have Kb? You have Ka, right? So you want to do the Kw over Ka. Okay. So that's 0.5 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5. After all those calculations, then you are going to get the value of 1.67 times 10 to the negative 5. Therefore, you know the POH is equals to negative log 1.67 times 10 to the negative 5. They're going to give you a value of 4.78. Therefore, your pH equals to 14 minus your POH, which is going to give you 14 minus 4.78. So you should have a value of 9.22. Okay, so this is actually how you solve this question, right? Again, you have a salt solution. You need to know what is the salt that you have. Okay, then you break apart your salt, and in the visualize and recognize. Okay, your Ki, okay, is neutral. Your Ni is basic. Therefore, you have a basic solution. Okay, therefore, you know you first need to compute the OH minus concentration using weak base equation. Then you calculate your POH, then the pH. Okay. So it's actually very similar. Okay. So what is the pH of this solution? Okay. Ammonium bromide. Okay. So this guy, right? When you see this guy, can you actually recognize this is CH3, NH3 plus, and then Br minus. Okay, that is actually the first thing that you do, because once you can write out this, you know Br minus is the conjugated base of a strong acid, right? Therefore, it's neutral. This one will be acidic, right? Therefore, you have a weak acid solution. Okay, since I have weak acid solution, proton concentration is equals to the weak acid concentration times your Ka. Okay, weak acid concentration is 0.422. Ka, again, you don't have Ka, right? You have Kb in this case. Therefore, Kw over your Kb. Okay, so once you do that, you are going to get a value 3.17 times 10 to the negative 6. Okay, therefore your pH equals to negative log 3.17 times 10 to the negative 6. Therefore, you get a value of 5.50. Okay, so it's actually basically the same as the question in the previous one, right? But just the previous one, you have a basic weak-based solution, but this one is actually weak acid solution. Okay. So it says at 25 degrees C, the solubility of the certain compound is certain molar solubility. I calculate the value of KSP at the temperature. Okay. So again, the keyword is actually solubility, right? So the first step for the solubility question is always write out the chemical equations, right? So the barium carbonate, okay, it's actually things that you probably need to actually have some sense. Okay. Barium is actually the Ba, okay, carbonate is actually CO3 2 minus. Okay, so that you know this one is BaCO3. Okay, and then it will dissociate. Once it dissociates, it becomes Ba2 plus CO3 2 minus. Okay, and this will be in the aqueous solution. Okay, and then you should know that the KSP equation will equals to the Ba2 plus times your CO3 2 minus. Okay. And you want to know the solubility of this guy, right? That means actually how much of that will actually dissociate. Okay. So then you start to actually look at the coefficients. The coefficient is always, in this case, is 1 to 1, right? Therefore, you know the Ba2 plus solubility will be S. The CO3 2 minus will be S, right? Therefore, you know your KSP will simply equals to S times S, which is actually S squared. Okay. The only thing you want to be careful is that you want to make sure when you compute your KSP, you must use the molar solubility, right? Then you check out the unit. Okay, it's mole per liter, right? So this is actually a molar solubility. That means actually you can just use it as it is. Therefore, this will just equals to 9.00 times 10 to the negative 5 times 9.00 times 10 to the negative 5. Okay, so when you do the computation, you're going to get 8.1 times 10 to the negative 9. And that will be actually your KSP. Okay, so this is actually how straightforward this type of calculation is. Okay, so the two things that you want to be careful first is that you always need to write out the proper chemical equation, right? Because once the coefficient change, the equation for your KSP will change accordingly, right? And then when you compute that solubility of each individual species, it will change based on the coefficient that you have. Okay. Second thing is actually you must use the molar solubility. Okay, so in this case, it's actually a simpler case, right? You actually already give you the molar solubility. So you don't need to actually do the conversion between the grain solubility to molar solubility. Okay, so this is actually how you solve the question number 13. Okay, question number 14. Okay, let's read through this one. Okay, the KSP of AgCl is this value. Consider a solution have certain concentration of CaCO2, certain concentration of AgNO3. Okay, so again, this is actually a very standard question you're going to encounter, right? In the first sentence of the question tells you the KSP of a specific species. Okay, and then the second sentence tells you the concentration of each individual product, right? So that is actually the typical structure you're going to see for this QSP type of questions. Okay. So again, the way to solve it is actually first write out the chemical equations. AgCl solid is going to become Ag plus Aq plus Cl minus Aq. The Ksp will equals to Ag plus first power Cl minus first power equals to 1.6 times 10 to the negative 10. Okay. So that's actually what you should actually write down from the first sentence. The second sentence will start to actually describe the concentration of these two terms. Okay. So you see, you have the much of CaCl2. Okay, so 1.0 times 10 to the negative 9 CaCl2. Okay, so if you become very experienced for this type of questions, okay, you will be able to say, apparently this one is going to ask you to provide you the information of your Cl minus concentration, right? And then you can see there's actual coefficient right here, right? It's Cl2. That means your Cl minus concentration will be 2 times 10 to the negative 9 N. Okay. The second species that you have is 1.0 times 10 to the negative 1 AgNO3. So apparently this one is going to tell you the concentration of Ag plus. Okay, so you can see the coefficient is 1, right? Therefore, your Ag plus will have a concentration of 1.0 times 10 to the negative 1 m. Okay. So once you have the information about the concentration of Ag plus, the concentration of the Cl minus, then what you do next is to calculate your QSP, right? And the QSP is actually compute this way, right? So Ag plus to the first power, Cl minus to the first power. Okay, there will be 1.0 times 10 to the negative 1 multiply 2 times 10 to the negative 9. This will give you a value of 2 times 10 to the negative 10. Okay, and then you can compare to that KSP. Therefore, we know the QSP is larger than your KSP. Therefore, you are going to see the precipitate. Okay, so it's the same logic. It's actually very similar to the things we actually went through previously. All right, that's actually how you solve question number 14. Okay, any question for this? Okay, so if not, let's do this one. 1 liter of saturated solution of CaF2 contains 0.016 gram of dissolved CaF2. What is the KSP of CaF2? Okay, so again, you know your target is CaF2, right? It's going to become Ca2 plus 2F minus. Okay, your KSP will equals to Ca2 plus to the first power, F minus to the second power. Okay, so that is actually always the first step. Okay, so since you want to know the KSP, right? Then you want to know, let's say the solubility of this guy is S. Okay, and then because the coefficient between your CaF2 and the Ca2 plus is 1 to 1, right? Therefore, you can actually write S here. For your F minus, you are going to write 2S because the coefficient is actually 1 to 2. Okay, therefore you write 2S here. Okay. With that being said, then you know your KSP will equals to S, 2S to the square, right? So once you have this, then you know what you're going to have is actually 4S cubed. So your KSP can be computed with this 4SQ equation. Okay. So now the question is actually, can you actually compute the solubility from the information you got from the question again, right? So what it says, you have that much of this guy dissolved in 1 liter, right? So what it says is actually the solubility will equals to, again, this will be the molar solubility. Okay, therefore we want to actually compute how many more of this species got dissolved, right? So it tells you the mass that got dissolved is 0.0167 gram. The molecular weight is 78.1 gram per mole. Okay, so when you do this operation, you got the moles of CF2 dissolved inside your solution. Okay, and it also tells you all these things actually dissolved in 1 liter of the solution, right? Therefore, you know the volume is actually 1. When you do these calculations, you can actually figure out your S is going to equals to 2.14 times 10 to the negative 4. Okay, so that is actually your solubility. Once you have this value, all you need to do next is actually just dump into this equation. Okay, therefore your KSP is going to equal to 4 times 2.14 times 10 to the negative 4 to the cube. Okay, and then once you do like computation, you should be able to get a number of 3.91 times 10 to the negative 11. Okay. So this is another type of question you're going to encounter. But again, it's the same way of solving the problem, right? You always need to actually write out the first equation. Okay, and then you also need to know how to write your KSP equation. Okay, then you should know, okay, if you translate into a solubility, how to write the things. Okay, and then you should know the solubility must use the unit of molar solubility. Okay, so that's all pretty much. All right, so any question for this one? Okay, next one. So it says, what is the solubility of CaF2 where the KSP is 4 times 10 to negative 12 in 0.35 N of NaF? Okay, so this again is a common ion type of calculation, right? So again, you know, CaF2 is going to become Ca2 plus 2 F minus aqueous. The KSP will equals to Ca2 plus times F minus to the second power. Okay, so if you look at, and then these things will equals to 4 times 10 to the negative 12. Okay, so let's actually what you get from this part. Okay, and it says if you put this salt in a solution, okay, so you have 0.035 M NaF. Okay, so if you look at this, and then together with the equation that you have, what this is going to tell you is that, okay, you're going to produce F minus with a concentration of 0.035 M. Right? So let's say the solubility of your Ca plus is S, F minus will be 2S. Again, this comes from the coefficient. This is actually 1 to 1. Therefore, we put S here. This is actually 1 to 2. Therefore, we put 2S here. Okay. And then in this specific solution, you know, you're going to produce a lot of the F minus, which is actually a common ion here, right? Therefore, you know, the Ca 2 plus concentration can be represented as S. F minus concentration will be 0.035 plus 2S. Okay, and then here we can always use small x approximation. Therefore, it becomes 0.035. Okay, so once you have these two, you're going to put this in there, put this in there. Okay, so you know S times 0.035 to the second power is going to equals to 4 times 10 to the negative 12. Okay, therefore you can solve your S, which is going to equals to 4 times 10 to the negative 12 divided by 0.035 square. And then you are going to get a value of 3.3 times 10 to the negative 9. Okay, so there will be actually the solubility of the CaF2. Okay. Next question. For which salt in each of the following group will the solubility depending on pH? Okay, so again, this is actual questions that you want to actually look at the anionic species. Okay, if it's actually neutral, then no effect. If it's actually a strong base or weak base, then it will be affected by the pH, right? So let's look at this. The anionic species here is actually F minus. This one will be Cl minus, right? So F minus is, I hope by now you should see this. Okay, F minus is actually a weak base, right? Cl minus is neutral. Okay, therefore you know this guy will be the one where its solubility will depending on the pH. Okay. Second, anionic species here is NO3 minus, right? This will be neutral because it's conjugate base of HNO3, right? This one is NO2 minus. This will be weak base. Therefore, it will depending on the pH. Everybody follow or I'm going too fast? Everybody's fine? So the key is actually you want to see the anionic species. If it is weak base or strong base, then its solubility will depending on the pH, right? Because pH is actually the one is going to introduce the extra H plus. Okay. If it's neutral, then it's actually no effects. Okay, so go back to this. This will give you the OH minus. This will give you Cl minus. Cl minus will be neutral. OH minus apparently is actually a strong base, right? Therefore, if you add in H plus, then the solubility of this guy will increase. Okay, next one. This will be NO3 minus. This one will be Cm minus. Again, this is actually the conjugate base of HNO3, therefore it will be neutral. This one will be the weak base. Therefore, it will be sensitive to the pH change. Okay, so those are the things that you should know. Once you see the things, then solving the sub questions become actually very straightforward. All right, so the very last question we want to go through today is this. So the KSP of this species is certain number. Okay, what is the solubility of Ag2SO4 in this specific solution? So again, it's actually a common ion type of calculation. Okay, we've done this for many times. Okay, again, starting by writing out the equations. Okay, the KSP will equals to Ag plus square multiply SO4 2 minus first power. Okay, and then this is going to equals to 1.2 times 10 to the negative 5. Okay, and then when we look at this equation, this species 0.25 m AgNO3. Okay, apparently this one is trying to tell you the Ag concentration that can be contributed from this specific solution. Okay, so hopefully by now you will see the Ag plus concentration will also equals to 0.25 m. Okay, so with this being said, okay, here you should know the solubility of your Ag plus will be 2s, SO4 2 minus will be S. Okay, so the total Ag plus concentration will be 0.25 plus 2s. The SO4 2 minus concentration will equals to just S. And we can use small h approximation. Therefore, this one will actually equals to 0.25. Okay. Once we have this, then we put it back to this equation. Therefore, 0.25 times S equals to 1.2 times 10 to the negative 5. Therefore, S is equals to 1.2 times 10 to the negative 5 divided by 0.25. Okay, there should be a square, sorry, 0.25 square. Okay, so once you do that, then you will be able to get an answer of 1.92 times 10 to the negative 4. And that's actually how you solve this question.